All right, welcome everyone. So today we're going to be talking about asymptotic notation and asymptotic analysis. This is generally the first lecture within your analysis and design of algorithms class. So let's go ahead and get started. As part of this, everything that we're covering today is all there in the textbook as well, pages 10 through 14. So any material that you want to check, feel free to find out there as well. Okay. So what we'll cover today is the asymptotic notation, big O, big omega, small omega, theta, etc. But before we get to that, what even is asymptotic analysis? So asymptotic analysis is essentially the analysis of the rate of growth of a function. And what we refer to when we say the asymptotic notation is to compare the rate of growth of two functions. Like when we say f of n is big O of g of n, we're trying to compare the rate of growth of two functions. So what we're trying to say, which function is growing faster than the other. One function may be larger than the other. The value could be larger at a specific value of x, or the input size n, which we're mostly interested in. But here what we're saying is we're essentially trying to determine which function grows faster than the other. And when we say grow faster than the other, in terms of the input size. In this specific lecture, we are focused on, and the asymptotic analysis, we are interested in how the function efficiency is in terms of as the input size grows, how much time does the function take? For example, if the array is size 20 versus if the array is size 20,000, how much more time does the algorithm need? Okay. So let's dive into it. Asymptotic notation, big O notation is defined as follows. We say that f of n is equal to big O of g of n if there exist two constants and not the threshold n and c, such that f of n is no larger than c times g of n for all values of n larger than n naught. Okay, so we are allowed to choose those two constants, and if we can find these two constants such that f of n is no larger than c times g of n, then we say that f of n is equal to big O of g of n. For example, if we're given that f of n is n and g of n is n square, then we would say that asymptotically f of n is equal to big O of g of n, because of course we can see that n is less than equal to n squared. Similarly, if we take another example, the polynomial here f of n is a0 n power 0, which essentially means 1, a1 n1, am n power n, then we can say that f of n is equal to big O of n power m. And this might be slightly less obvious, but we will prove this as well, at least via an example. Similarly, there's the corresponding big omega notation, which is not a new definition in this sense. It is just simply the reverse of big O notation. So for example, when we say that f of n is equal to big O of g of n, we can equivalently say that g of n is equal to big omega of f of n. And we can also say directly without referring to the big O definition by saying that g of n is equal to big omega of f of n. Again, if we can find two constants such that g of n is greater than equal to c times f of n for all values of n greater than equal to n naught. In this case, the n naught represents the threshold value. As you notice that the asymptotic notation and the asymptotic analysis is trying to talk about the rate of growth. The word asymptotic comes from a Greek word asymptotos, which essentially says which refers to the asymptote. In this case, the value of the function as it approaches infinity. That's what we're trying to compare these functions to. Okay, so of course we can see that as n becomes very large, f of n is much smaller than g of n, and of course f of n is also growing slower than g of n here. So when we're doing big O notation, or really any asymptotic notation, we may be interested in the graph perspective just to see, we graph those two functions and see how they compare. Here, for example, we have drawn out the f of n in the orange colored, the one that has lower values towards the higher values of n, and the gray one, which represents g of n. So what are we plotting here? We're kind of comparing the values of f of n for different values of n. So n here represents the input size, could be the array, could be any other numbers, how many numbers you gave, etc., etc. So if the input size was 80, f of n took this much time or these many operations, g of n took sorry, f of n took this much time, g of n took this much time, but when you had an input size of 250, f of n took this much time, about 4,000, g of n took more than almost 6,000. So that's what we are comparing here. And of course, in this case, visually, we can see that g of n is growing faster than f of n, or at least we are able to see visually that f of n grows no faster than g of n. So it would meet our definition that f of n is equal to big O of g of n, even though in this case we are not really focused on finding the constants c and n naught, because we don't have the definitions of f of n and g of n, but visually we're able to compare that. Now, one distraction that we must dispel early, first things first here, that what's an item in a set versus the set. We are usually clear about it. For example, when we say an item X is in the set S, we say X is in the set S using this in symbol. Similarly, a set can also be a set of functions. So we would say function f can be in the set S just the same way, and this is how we would write. Now, sometimes for shorthand, some people might write f is equal to s, as long as it's clear to us from the context that what they're really saying is that f is in the set S. Now, this might be confusing on why we are giving this example here. The reason is that the example where we do that exactly is in the asymptotic notation. When we say that f of n is equal to big O of g of n, what we are strictly saying is that big O of g of n, because the big O of g of n is a set of functions that grow no faster than g of n. So what we're really saying is that f of n is in that set of functions that grow no faster than that. F of n is just a function, it's not a set. So when we are saying that f of n is equal to big O of g of n, which most computer scientists and mathematicians are comfortable writing, strictly speaking, what they're saying is that f of n is in the set of functions that grow no faster than g of n. Okay, so assuming this distraction and this shorthand notation is clear, we can continue. And one might imagine that the reason this shorthand notation is relatively popular or relatively common, or even if you call it a misuse or an abuse of a notation, is because, of course, in common emails and text and all that, it's difficult to type in the in symbol all the time. We can write it here, but then you have to insert symbol, or if you're using LaTeX, then of course you have to do something. While we can simply just write equal to, it's available in any keyboard, and as long as it's clear from the context. So that's really it. It's only because it's a shorthand notation, that's why people don't mind. But just be aware that big O on any asymptotic notation is the set of functions. When we are saying a function is equal to that, we are just saying that function is in that set. Okay. Let's continue on here. So let's go to the next asymptotic notation. That's called the small o notation. The small o notation goes as follows. We say small o notation, f of n is equal to small o of g of n. If for any constant c greater than 0, there exists constants n naught and c. For any constant c greater than 0, there exists a constant n naught such that f of n is less than c times g of n. So if we contrast the small o notation with the big O notation, there's one easy difference to spot, that f of n is strictly smaller than, but there's a more important basic difference that we must spot, which is that in the case of small o, this inequality can be shown even if a constant is given to us. That means a constant is being enforced upon us, and still we can find a threshold value of n naught such that f of n will still become smaller than c times g of n. For example, somebody could give us a very small value of c, and now for a little bit f of n becomes larger because g times n is being g of n is being multiplied by a very small constant. F of n could become larger than that, but as you go to a higher value of n, eventually f of n is going to become smaller. And if that is the case, that's when you are saying that f of n is growing strictly slower than g of n. That's what we're really trying to say with the small o notation. So if f of n strictly grows slower than g of n, then even if you try to scale it up a little bit by multiplying g of n with a very small value, eventually for a high enough value of n, you're going to see that the f of n again becomes smaller because it's growing slower. That's what the small o notation is all about. Now, correspondingly to the small o notation is the small omega notation, which again is just the inverse. If you understand the small o notation, you understand the small omega notation and vice versa. You can actually live out your entire computer science life without using one or the other notation, as long as you use the other one in the other direction. So if you just want to use the small o notation, perfectly fine. You might have to just switch the directions on which one you're saying, but because small o notation, small omega notation are essentially equivalent, for that reason, it's helpful to know both. When we say that f of n is equal to small o of g of n, we are essentially saying that g of n is equal to small omega of f of n. And similarly to the big omega notation, you can also write small omega directly using a similar concept without writing it in terms of small o. As a quick example, we can say that n is equal to small o of n squared, as we have seen, because of course, no matter how small a value that you multiply with n squared, eventually the n squared, even if you multiply with 0.001, eventually is going to exceed n for a high enough value of n. And that's because n grows slower than n squared. Similarly, n cube and n squared grows slower than n cube. So n cube is equal to small omega of n squared. And like we just said, that means n is in the set of functions that grow slower. So n is in the set small o n squared. And similarly, n cube is in the set of small omega n squared. But we write equals here for shorthand notation. And now that brings us to the last and the final asymptotic notation, which is called the theta notation. The theta notation essentially says that if one function grows no faster, the other function grows no faster than this, then they have the same rate of growth. We call that to be a theta function. So that's the theta notation. You can write the theta notation as a small theta or the big theta, but they mean exactly the same. You can mix and match at any time, perfectly fine. Small o and big O mean different things. Small omega and big omega mean different things. Theta notation just means the theta notation. So in this case, we're saying that f of n grows no faster, g of n grows no faster. So f of n is theta of g of n. That's all the asymptotic notations we have here. So let's review them one more time. F of n is equal to big O of g of n. That essentially says that g of n is equal to big omega of f of n. F of n is big O of g of n, and g of n is big O of f of n. That then they're the theta of each other. F of n is small o of g of n. That means that g of n is small omega of f of n. And now one final addition here we must claim is that if we say that f of n grows slower than g of n, so f of n is equal to small o of g of n, then we make the conclusion that means once you go to a high enough value of n as limit of n tends to infinity, f of n divided by g of n, that will be 0. And that's really the asymptotic part of the asymptotic analysis here. Okay. Let's do a little bit more practice. Let's try to prove a big O relationship, small o relationship. So when we want to find a big O relationship, all we have to do is we can simply find the constants C and N naught. Any constants that work. You don't have to find the best ones. Not that there is a best one, but you might think that, oh, I should find an interesting one. It doesn't really have to be. You can find any values of C and N naught. Your claim is proven, and that's all that's needed. For example, let's suppose that we have f of n is equal to 47n plus 83n squared. G of n is equal to n squared. We want to prove that f of n is equal to big O of g of n. Firstly, we observe that f of n is actually larger than g of n. But remember, big O notation is about the asymptotic analysis, asymptotic notation. So we are not talking about whether the function is larger or smaller. We're talking about the rate of growth. Turns out that they both grow at the same rate. So f of n doesn't grow any faster than g of n. That's all we're trying to prove. So to prove that, we can argue that 47n plus 83n squared, which is f of n, is no larger than 130 times n squared. And obviously, you can observe that 130 is the sum of these things because this is an easy inequality for us to prove. And now we easily have those two constants. C is equal to 130, n naught is equal to 1. And therefore, by definition, f of n is equal to big O of g of n. You could have chosen a different values as well here. You could have said C is equal to 1000 and naught is equal to 2. In that case, also it's true, so it's perfectly fine. whatever values of C and N naught that you can choose such that f of n is less than equal to C times G of n for all values of n greater than N naught, the threshold value, you have the result that f of n is equal to big O of G of n. Similarly, we can also use a small O notation, but in the small O notation, other than some very simple examples, you could easily run into a case where it is not that straightforward to prove using this constant and the threshold value. So in that case, instead what you can do is you can use the L'Hopital's rule, and like in the previous slide when we mentioned that f of n is equal to small O of G of n implies that the limit as n tends to infinity is going to tend to 0. So you can actually use that to your advantage here. And let's suppose we want to prove this function here, log of n whole cube plus 3 of log n whole square is small O of square root of n. What we're trying to say is that this function grows slower than this function. Now, there's a little complicated expression here. So if we try to just simply use C and N naught, it gets really out of hand very quickly. So what we would rather say is, let's try to find the limit of these functions, this divided by this, as n tends to infinity. Okay. Now, we cannot easily find that either. Both the numerator and the denominator tend to infinity, but we can use the L'Hopital's rule, which says that the limit of these two functions, assuming they are both continuous and differentiable and they both tend to infinity, then you can simply take the differential on both sides, and that's what we do here. So if you take the derivative carefully, you will see that the derivative of this is this, and you have to take the derivative of the denominator as well. So here I have n power 1 by 2, and here I have n power 1 by 2. So it may appear that as if I forgot to take the derivative, but not quite. Actually, if you take the entire derivative of this side, because 1 by n comes from this side as well, so that's the reason. So you have to do your steps carefully here, but this is what the expression comes out to be. We still cannot solve it, but we can take the differential again. We can take the differential again, and finally we can see after a few steps here, we can see that this becomes 0. So that means that this is small O of f of n is small O of G of n. So when we have this asymptotic notation, we can actually try to do a little analogy with real numbers. Functions are not real numbers. A function is a function. A real number is a real number. But still, we can try to do a little analogy here for intuitive understanding. And we could say that big O is kind of like saying less than equal to. Small O is kind of like saying less than. Theta is kind of like saying equal. Small omega greater than, big omega greater than equal to. And this can sometimes help us with that. Now, we can also think if these asymptotic notations follow the same properties that we are used to. For example, we have transitivity. When we say x is less than y, y is less than z, therefore x must be less than z. And something similar applies here, but it's not exactly the same. So we can think about which properties apply to these asymptotic notations, because big O is a little analogous to less than equal to, but it's not exactly that. So we still have to check whether these properties hold and not hold. So once we review this further, we see that the transitivity actually does hold. So when you say f of n is equal to big O of G of n is equal to big O of h of n, then f of n is equal to big O of h of n, and you can prove that. And similarly, you can prove that for all the asymptotic notations. The reflexivity is for greater than equal to, less than equal to, equal to. Symmetry is for equal to. Transpose symmetry is, that's how we had defined it. So this part is straightforward. However, there's also trichotomy property which holds to real numbers. For example, when we have real numbers, x and y, we can always say that either x is less than y, or x is equal to y, or x is greater than y. But for functions, we're not able to say that. We're not able to say that every time. You may be able to compare them, but maybe you can't compare them in terms of small o and small omega and theta. You have f of n is equal to sine n, g of n is equal to cos of n. In this case, neither function is a small o of other, neither of is small omega of other, neither function is a theta of other. We're simply not able to compare these functions. Sometimes one is higher, sometimes the other is higher, and they keep going through a cycle. They are trigonometric functions. And even if you limit yourself to non-trigonometric functions, you can still come up with examples that two functions cannot be compared. So trichotomy does not apply to asymptotic notation, even though it does apply to real numbers. When we're given two real numbers, we can say that one of these three things must be true, but not for functions. That's really all. That's all we have about asymptotic notations, at least. A lot of the algorithmic portion is left. Just in case you're interested about what is the etymology of the word asymptotic, like I mentioned, comes from the Greek root. There should be a video floating around somewhere. Oh, that's all we have for today. Keep learning. Have fun.